All right, ignore the glare. Normally I put a piece of paper there, but I need to write in that spot, so it's going to be glaring at you. I'm going to work through how you would fill in an orbital diagram, and then from that be able to determine the number of unpaired electrons, a set of 4 quantum numbers for the last electron filled, and then from the orbital diagram how you would write an electron configuration. So I'm going to work through 3 examples with 3 different elements. To start with, I'm going to do element number 106, which is Seaborgium. All right, that's element 106. So that means in its neutral state, there are 106 protons and there are 106 electrons. Now for this element, it's pretty unstable. All the atoms we've actually detected of it have been man-made. So we're making our best guess based on the element that comes above it in the periodic table, tungsten, and filling in the pattern. That's all you're going to be graded on for this class anyways, is if you can follow the pattern and the rules for filling, not any weird exceptions or things like that. All right, we got 106 arrows to fill in, so we'll follow the rules for filling in our electrons. Remember, our arrows are representing our electrons, and we do an arrow up or an arrow down. So we start at the bottom and work our way up. So 1s is the lowest energy, so we'd start by drawing in 1 electron going up, 1 electron going down. This has to be filled before we can move on to the next one. So we do 1 going up, 1 going down, and then the next lowest is the 2p. There are 3 separate 2p orbitals. Each line can hold 2 electrons, and you always want to do 1 per line first, and then you start to double fill them. All right? So up to now we've got 10. We only have 96 more to go. So let's see, we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 20 electrons. After the 4s comes the 3d. There are 5 d orbitals, each holding 2 electrons, which means you can hold a total of 10 electrons in a d sublevel. So after 4s, we fill the 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now we've used 30 electrons. After 3d, the next lowest is 4p. 1, 2, 3, 4, 5, 6, 7, 8. And then after 5s comes 4d. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, so that's another 18. I'm losing track. That's 48 total electrons so far, okay? So after the 4d comes the 5p. 1, 2, 3, 4, 5, 6, and then the 6s. 1, 2, so that's another 6. So, 6 plus 2 is 8. So we're at 56 electrons so far. And this is where it starts to get tricky because those energy levels are a little bit tighter together. So now you'll go to the 4f because that's the next lowest, then the 5d, then the 6p, then the 7s if it's necessary. So you'll keep working your way through. Notice we don't do all the 4s and then all 5s because that's not the order that they fill in. We go in lowest energy first. So we're on to here. So this is 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70. On to the D, 71, 72, 73, 74, 75, 6, 77, 78, 79, 80. All right, over to the 6P, 81, 82, 83, 84, 85, 86. All right, then the 7S, 87, 88. So we're at 88 electrons. Again, after the 7s comes the 5f because it's the next lowest in energy, and that's the order that you have to fill them. So we're on to the 5f. We're at 88 electrons. 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102. So we're at 102. We only have 4 electrons left. The next sublevel is 60. This is where following the other rule, like Hund's rule, is really important because you want to put 1 per line first before you double them up. So we have 4 more left. 1, 2, 3, 4. That is the orbital diagram for the expected electrons within Seaborgium. So this is our representation of where we're likely to find the electrons. All right, next, number of unpaired electrons. You now look at your picture and you find any spots where there's just one arrow per line. Anything that's empty doesn't count. You're just looking for just a single arrow. So in this image, we have 1, 2, 3, 4 unpaired electrons. All right? Now, quantum numbers. So now we want to assign a set of 4 quantum numbers to the last electron we drew. This one right here is the last electron I wrote in. So those are the set of 4 quantum numbers I'm going to come up with. So the n is the number in front. That is your energy level. That's your principal quantum number. So this number here is your value of n. So for this Seaborgium, our n value is 6. Because we were filling in those last electrons in the 6d sublevel. For the L value, it comes from the letter. So for this, it is the letter D, which we tie to a value when we talk about this. S is 0, P is 1, D is 2, and F is 3. So since this is a D, my value of L is 2. Right? The value of L dictates what your possible values of M sub L can be. So in this case, since L is 2, M sub L can be -2 up to +2 and every small number in between. You could go in order and sort of label these with those values, -2, -1, 0, +1, and +2, and then give the number designation of whichever line you landed on. So we could say +1, but technically assigning those to those places is really arbitrary. Those orbitals are said to be degenerate. They're of equivalent energy, so putting 1 in a specific place is kind of just me following an order rather than an actual product of that one is specifically that value for a quantum number. And then finally, did you draw your arrow going up or down? Again, totally arbitrary which way you start, as long as within each orbital you have one going up and one going down. So since I drew it going up, I'll put +1/2. If I had drawn it going down, I would do -1/2. All right, and then lastly, we write our set of 4 quantum numbers, we did that. Now we're going to write our electron configuration. So you basically name the orbital, or name the sublevel, and then how many electrons are in that specific sublevel. So we start at the bottom with 1s, and we drew 2 arrows. Next is 2s, and we drew 2 arrows. Then comes 2p, we drew 6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. See, I'm just following in order. Next comes 4d10, 5p6, 6s2. After 6s was the 4f, 4f14, 5d10, 6p6, 7s2, all the way over, 5f14, and then finally 6d1, 2, 3, 4. So that is your complete electron configuration. This is just a shorthand version of the orbital diagram. This is what we're going to start to get straight from the periodic table. So you won't have to fill in all these arrows and do it. You'll just be able to go right from the periodic table and write it out from there. Okay? A couple of other things. Notice that if it is filled, which everything up until the last sublevel should be, because that's the rule, you have to fill one sublevel before you can move on, then the numbers at the top are the maximum number of electrons in that sublevel. So for an S, that's 2 maximum. For a P, it's 6. For a D, it's 10. And then for F, it was 14 was the maximum. So if you're completely filled, it should be that value.